In the modern world, sustainability is extremely important. Cities are becoming more polluted and overcrowded, and one needs to only look at the roads to see this. When looking at Sydney in peak hour, a small journey of only 5 kilometres through CBD can take more than half an hour to be completed. This works out as an average speed of about 10 kilometres per hour, which is faster than walking speeds, but is still very slow in the grand scheme of things. These types of journeys, therefore, are perfectly suited to bikes. We've all experienced start-stop traffic congestion at peak hour, and it is an endless source of frustration for so many. Recent data from various national studies highlights the inefficiency of metropolitan commuting, which is a design and infrastructure problem that permeates many fields of engineering and other technical research. The Peak Organisation of Australasian Road Transport has published a report which notes that Sydney commuters actually face around 30 to 40% increase in travel time during peak hours and weekends. The report further discloses that 88 to 98% of this congestion is due to the asymmetry between road users and road capacity. Electric bikes are an increasingly popular method of commuting, with electric bike sales up 145% in the US over the last 2 years. Wide use of commuting via electric bikes has the potential to radically change the current traffic congestion and commuting inefficiencies currently prevalent in populated areas. However, a large proportion of commuters are still hesitant to use electric bikes due to the inefficient range, speed, and perceived danger of the current bikes on the market.
The average commuting distance is 4 to 8 kilometres for those who live and work near the Sydney CBD, and according to the Australian Institute, the average travel time for commuters is 4 hours and 12 minutes a week. Employees who work more days per week and those with higher salaries tend to have longer commuting times than others. Inefficient commuting places unnecessary strain on the potential free time of these already time-poor commuters. More than 10% of parents in paid employment spend more time commuting than they do with their children. An efficient electric bike would free up extra time in the week for them to do more important things, such as spend time with their family. Our solution incentivizes bike travel by implementing a novel energy harvesting device to increase the range, speed, and safety of an electric bike. The use of our product would simultaneously decrease an individual's commute time and, on a larger scale, reduce traffic congestion. Alongside recharging the primary battery, the harvested energy is capable of powering necessary safety features such as lights.
Some of the biggest barriers that prevent people from cycling are the inconvenience of having to sustain physical effort and the safety issues associated with riding. This is where an energy harvesting system could prove valuable, taking otherwise wasted energy and converting it to useful power. In this way, features of a person's riding could be to reduce the physical effort required and allow for safety features such as lights and indicators to be powered by a person's riding instead of being powered by the battery, removing the risk of the battery running flat, leaving the rider with no lights.
More than a third of New South Wales population cycle each year, majority of which do so for recreation. Of those that cycle for transport reasons, surveys suggest that approximately 10% are commuters and another 10% travel for education. These branches of the Australian biking community share many customer characteristics whereby the customer needs overlap. For example, these individuals all consistently rely on their bikes and thus need safe operation and desire durability. Broadly, the target market is existing and the potential cyclists aged 16 to 50 that are interested in energy efficient and novel bike attachments that incentivize and complement the commuting experience. This group of consumers can be represented as through their actions expressing environmental, financial, and health concerns, all of which contribute to the defined target market.
Standard wind turbines cannot be easily integrated into the frame of a bike, and so our design uses a model of a roof vent to generate electricity. The turbine is 0.3 meters in diameter and 0.15 meters in height, and is to be placed centrally in the front wheel of an electric bike.
Standard bicycle designs do not have enough hub space to integrate any wind turbine capable of generating sufficient energy. This space is limited by the presence of spokes that connect the hub to the rim, and although they seem like a necessary component, there are alternative methods of facilitating the wheel's rotation. Freeing up the entirety of the space in the front wheel, our team developed a modified spokeless wheel that connects the rim directly to the fork of the handlebars. Using a series of bearings, the tyre can be made to move while the hub remains stationary.
The turbine's rotational energy is converted into electricity, which is then stored in a lithium-ion battery, recharging the e-bike and acting as a power source for both the front and tail lights. With improved battery specifications and safety features, bike commuting becomes a more viable option for many metropolitan residents. Taking inspiration from millions of years of natural biological engineering, the material in our design is designed to mimic fish scales to reduce drag and turbulent flow. These conditions are preferable for the operation of the turbine and thus promote efficiency.
While our proposed design of using a roof vent on a bicycle may sound far-fetched, it's an innovative and effective way of harnessing wind energy from a moving vehicle. Normal wind turbines are oriented to harvest energy from one primary direction. However, our design allows our wind energy to be harvested from multiple directions. The quasi-spheroidal shape captures any crosswinds and tailwinds, as well as making use of the apparent headwind. The turbine is connected to a set of magnets and coils that constitute an axial flux generator. The top and bottom plates of the turbine are fixed to rotate with the blades, and by positioning the magnets to direct fields through the wound coils, this motion induces a current. More specifically, this low starting torque generator embeds 10 pairs of neodymium magnets into aluminium plates, which rotate around 10 cells of 16-gauge copper coils wound 32 times each.
To calculate the possible output of our system, we first took the average front-on wind speed experienced by riders as the upper limit for the turbine's tangential velocity. Although Betz's law asserts that this kind of kinetic transfer can be a maximum of 59.3% efficient, given enough time, the turbine would reach this speed. Taking into account energy losses, we calculated the angular velocity to be 31.5 radians per second with a period of 0.2 seconds. Using this information and the generator features described earlier, by Faraday's and Ohm's law, the predicted maximum power output is 1.026 kilowatts at 24 volts. This energy will be used to charge a secondary battery with a 3.5 amp hour capacity. It connects to both the safety lights and the bike's 11 amp hour primary battery. When fully charged, it will be capable of powering the 12-volt LEDs for almost 7 hours, with all unused generated energy being redirected to charge the primary system. To optimize performance and prevent damage to components, the charging current for this battery was chosen as 1/10 of the amp hour rating. With these parameters, operating at maximum power output, it would take just over 13 hours for the secondary battery to be fully charged by the energy harvesting system.